24 billion kilometers from Earth, November 2023. The Voyager 1 probe suddenly begins returning unreadable telemetry. The mission is in critical danger. NASA engineers trace the issue to corrupted memory within the flight data subsystem. With no way to physically replace the chip, the engineering team meticulously relocates and splits the critical code into healthy memory regions, successfully routing data around the dead silicon to restore engineering readouts. This story is a perfect reminder that in electronics, reliability is never an accident. It is the direct result of a continuous battle against wear and fundamental physical limitations. And today, we are going to dive deep into one of the key factors behind this exact reliability: correctly calculating your voltage margin. Welcome back, friends. You are watching High SNR. There is a very old, very persistent myth in circuit design. It says that voltage margin is just some magical constant. Just multiply your supply voltage by 1.5, or maybe 2, pick a MOSFET, and sleep peacefully. The developer's logic usually sounds pretty convincing. If my circuit is dealing with dangerous voltage spikes, I will simply drop in a MOSFET with plenty of headroom. For instance, a 200-volt part for a 48-volt line. Better safe than sorry, right? Spoiler alert. This is exactly the kind of situation where better safe than sorry will actively destroy your design. And it hurts a lot. In this episode, we will break down exactly why simply dropping in an oversized transistor rarely solves your underlying transient problems. We will uncover what you are actually paying for when you specify high voltage components. And we will analyze completely different safety margin strategies across 3 completely distinct engineering domains. Let's get started. Section 1. The price of fear. When safety margins become a burden. Let's return to that phrase from our section title. In power electronics, over-specifying components is easily one of the most dangerous misconceptions you can have. Leading silicon manufacturers consistently warn against overestimating your breakdown voltage ratings unless absolutely necessary. In fact, many application notes make the same point. Blindly increasing voltage margins is an engineering mistake that often leads directly to degraded converter performance. Why is this? The answer is simple physics. In conventional silicon high-voltage MOSFETs, you always pay the price for a higher breakdown voltage directly in the drift region. This results in an increased on-state channel resistance, commonly known as RDS on. To allow a transistor to block a higher voltage, manufacturers must physically design this drift region to be thicker and less heavily doped. All else being equal, the specific on resistance scales roughly with the breakdown voltage squared, up to the power of 2.5. This is known as the classic silicon limit. Because of this catastrophically nonlinear relationship, doubling your voltage rating can easily push you into a several times higher static channel resistance. Sure, your overrated transistor might easily survive a transient voltage spike, but because of that massively increased channel resistance, it will now generate significantly more heat. You have just traded a voltage failure for a highly probable thermal destruction of the silicon die. Unless, of course, you try to buy your way out of this higher resistance by selecting a larger silicon die. But if you do that, your parasitic capacitances will absolutely skyrocket. The transistor will become sluggish, and you will pay for it with enormous dynamic switching losses. An oversized voltage margin is exactly the kind of baggage that weighs down your entire design and can even completely break it. With that fundamental trade-off in mind, let's establish a unified metric: the voltage derating factor. Simply put, this is the percentage of the component's absolute maximum rated voltage that it actually experiences during normal circuit operation. Now, let's examine how this optimal percentage shifts across completely different engineering sectors. Section 2. High-power applications. Industrial motor drives. Let's begin with heavy-duty industrial environments. When driving highly inductive loads that generate massive back EMF spikes, like large motor drive inverters or heavy solenoid controllers, the standard practice is to derate your transistors to a maximum of 50%. In other words, the transistor's rated voltage is chosen to be exactly double the nominal DC bus voltage. In this industry, engineers strictly adhere to the IEC series of standards. The interesting thing about industrial standards is that they rarely mandate a specific derating percentage directly. Instead, they impose brutally strict requirements for overall system safety, high voltage isolation levels, and the system's ability to survive massive transient events. So, how does this actually dictate your transistor's voltage margin in the real world? Well, the standard demands that an inverter must absolutely survive the sudden emergency braking of a heavy CNC machine or an elevator. During such an event, the motor enters regenerative mode, converting mechanical kinetic energy into electrical energy that flows through the inverter into the DC link, charging the bus capacitors and driving the DC bus voltage upward. Because that regenerative energy has nowhere else to go, it aggressively charges the main filter capacitors. The bus voltage rapidly spikes from a normal operating level of 540 volts all the way up to the over voltage protection threshold, which is typically set at 800 or even 900 volts. A standard 650-volt silicon switch has essentially no margin there. It will likely avalanche, overheat, and fail under those conditions. Therefore, designers are forced to specify inverter switches rated for 1200 volts. Fortunately, space is rarely an issue inside a large industrial control cabinet. You can easily afford to ignore the terrible switching losses, bolt the transistors to a massive heatsink the size of a cinder block, and cool the whole assembly with high CFM industrial fans. In this specific scenario, paying the massive penalty for high-voltage silicon and accepting the resulting thermal losses is not just blind obedience to some magic ratio. It is a calculated and completely justified premium for rock-solid fault tolerance in heavy industry. Section 3. High-density applications. Compact DC-DC converters and telecom. Now, try applying that exact same 50% derating rule to a handheld gadget or a high-density server power supply. It would be an absolute thermal disaster. Let's move into the realm of high-efficiency, highly compact power conversion. Remember that massive increase in on resistance we talked about earlier? In a high-density environment, that extra heat will simply melt your circuit board. In this sector, designers strictly follow the IPC-9592B standard. Under this guideline, a transistor is safely allowed to operate at up to 80% of its absolute maximum voltage rating. That leaves a safety margin of merely 20%. Engineers here cannot simply brute force the problem by dropping in higher voltage parts. They must meticulously optimize their PCB layouts and tightly control their transients, allowing them to stay within these rigid limits and leverage highly efficient, low-voltage silicon. Section 4. Aerospace and Deep Space Applications. The Ultimate Frontier. That brings us exactly back to our opening story. The fact that the Voyager probe operated flawlessly for nearly half a century in deep space before a critical hardware failure was absolutely not a stroke of luck. It was the direct result of paranoid, meticulous adherence to extreme reliability standards. In this third engineering reality, the aerospace sector, NASA derating guidelines strictly dictate that a semiconductor switch must never experience a voltage exceeding 75% of its rated maximum. Outside the protective shield of Earth's atmosphere, silicon devices are constantly bombarded by high-energy protons and heavy ions. When a cosmic particle punches through a silicon die at a substantial fraction of the speed of light, it triggers a localized, instantaneous microavalanche event. If the bias voltage across that transistor is too high, this tiny disruption instantly cascades into an uncontrollable thermal runaway, literally vaporizing the silicon substrate. The lower the applied voltage across the junction, the vastly higher its chances of safely absorbing and surviving a high-energy cosmic strike. Therefore, maintaining a derating factor strictly below 75% is not just being overly cautious. It is literally the only mathematically viable way to keep digital logic and power electronics functioning in the intensely hostile radiation environment of deep space. Section 5. The anatomy of a voltage spike and the engineer's true arsenal. So, if we are not building a probe for deep space, and we are not wiring up a heavy industrial factory floor, how do we safely maintain that aggressive 80% voltage load in a compact design without incinerating the board? The secret is to aggressively suppress the voltage spikes at their source, rather than just endlessly increasing the voltage rating of your components. The peak voltage seen at the drain of a turning-off MOSFET is not just the DC supply voltage. It is the supply voltage plus the magnetic energy stored in the parasitic loop inductance, which generates a massive counter-electromotive force, or back EMF. The fundamental equation is straightforward. The absolute peak drain voltage equals the main DC supply voltage plus the product of the total parasitic loop inductance multiplied by the rate of change of current, or dI over dt. At modern nanosecond switching speeds, Even a single, poorly routed centimeter of PCB trace can possess enough parasitic inductance to generate a lethal 100-volt inductive kickback. This brings us to the engineer's first true weapon, tuning the gate drive circuit. By carefully increasing the value of the external gate resistor, you deliberately slow down the charging and discharging of the MOSFET's internal parasitic capacitances. This slightly reduces the di over dt rate, which in turn dramatically reduces the inductive spike, smoothly rounding off the transient peak. However, this requires absolute surgical precision. Slow it down too much, and your dynamic switching losses will go through the roof. Next is tool number 2, snubber networks and active clamping topologies. The oldest, most reliable method is the classic RC snubber. It essentially absorbs the high-frequency ringing energy and dissipates it harmlessly as heat through a resistor. But the modern high-efficiency solution is the active clamp topology. By utilizing a dedicated auxiliary switch and a clamp capacitor, we can capture that destructive inductive energy, strictly limit the peak voltage, and actually recycle that energy right back into the load. Mastering these techniques lets you pick the right voltage rating, not the biggest one. But tight margins are earned, not assumed. Layout, clamping, and high-bandwidth worst-case validation are non-negotiable. As you can see, selecting the right silicon is never about blindly following a rule of thumb. It is always a meticulous search for the perfect engineering balance. But you already know that, so let's wrap this up. The final checklist. To bring it all together, let us build a quick checklist for properly selecting the right MOSFET for your next critical project. Rule number 1. Oversizing will hurt your design. Always remember the classic silicon limit. If you choose a transistor with double the required voltage rating, you will automatically generate several times more conduction losses out of nowhere. Never exceed the required voltage rating without a solid mathematical justification. Rule number 2. Context is absolutely everything. In an industrial motor drive, derating to 50% is purely a matter of basic circuit survival. In satellite design, derating to 75% protects against cosmic radiation. But if you are designing a high-efficiency compact power supply, your absolute target should be the strictly controlled 80% limit. And rule number 3, attack the root cause, not the symptom. Stop trying to hide bad layouts behind massive, slow, overheated, high-voltage silicon. Suppress the transients at the source. Optimize your gate drive resistors, tighten your PCB layout, or implement active clamp topologies to tightly regulate those voltage spikes. And if you are pushing margins past 80%, always back it up with rigorous, high-bandwidth validation. True reliability is never achieved by just picking bigger parts. It is achieved entirely through meticulous, intelligent engineering. Keep routing those traces tight. Always read your datasheets from cover to cover, and I will see you in the next one.